Assalamu alaikum. So, yesterday we talked about the effect of temperature on the rate of chemical reaction. So, in continuation to that topic, because the topic is important and it's a lengthy topic, effect of temperature on the rate of reaction. On the rate of reaction. So, we just have studied the effect of the variation of uh, activation energy EA is a function of rate constant ratio K2 or K1, and we have also shown that the effect of temperature variation on the change in the rate constant ratio. So today we will study the those kind of reaction for which the change in temperature uh, cause a huge deviation from a linear behavior or heinous behavior. So, and also we have to study the effect of temperature on equilibrium system in terms of entropy change, enthalpy change, and Gibbs free energy change. So the first thing we have to focus on that is the uh, how which kind of relationship will be applicable for those kind of reaction which show a non-linear behavior of ln k versus 1 over t. So this is shown that for this kind of reaction, the velocity constant or the specific rate constant is a function of temperature raised to a constant. So the specific rate constant is a function of temperature raised to a power n, where n is an integral number or half integral number, so or a fraction number. So in the Arrhenius equation, we have the Arrhenius equation exponential form k is equal to a e raised minus ea over RT. So this equation we have to introduce another term k is equal to a t for n e raised minus ea over RT. So this equation will be applicable for those kind of reaction which are studied over a wide range of temperature, or in log term this can be written as ln k is equal to ln a plus n log t minus ea over RT. So this is some kind of relationship. It's important for today. K is equal to a t power n e raised minus ea over RT, or in log term ln k is equal to ln a plus n log t minus ea over RT. So these are some kind of important relationship for today, 1 and 2. In addition to these relationships, we have to study the effect of temperature on equilibrium system, effect of temperature on equilibrium system on equilibrium. So for example, we have a system A plus B, it's going into product C plus D, and C plus D product then recombine and making the reactant. So the forward rate constant is represented with K1, and the reverse rate constant is represented with K minus, so there is K inverse. We know that the rate of forward reaction is proportional to K1, the concentration of reactant A into B, and rate of reverse reaction or RB or or rate of reverse reaction is equal to K inverse, and the reactant or C, and in this case D. When the system is at equilibrium, we have rate of forward reaction RF is equal to rate of reverse reaction RB. So just putting the value, so K1 concentration of A to concentration of B is equal to K inverse concentration of C into concentration of B, or just rearranging K1 over K inverse is equal to C concentration of D divided by concentration of A concentration of B, and this is actually the equal to the rate constant or equilibrium constant K. So this is one kind of relationship. K is equal to K1 divided by K inverse is equal to concentration of product divided by reactant. Now we know from our Arrhenius equation, just applying general Arrhenius equation, that is ln K is equal to ln A minus EA over RT. Just differentiating this equation with respect to temperature, so d log K over dt is equal to d ln, so this will give you 0 because this is a constant, and minus d over, we have to take the constant outside, so minus EA over R is constant, and we have to differentiate this d over dt, and this is T inverse. You already know the general formula that if we have dx power n over dx, so we can write down n x power n minus 1. So from this we are getting minus, from applying this formula we can get from this minus 1 over t square. Just putting this, so we have this relationship that we have to write down here, d log K over dt is equal to, the minus minus will be plus, so we have plus EA, and this EA now we have, for the equilibrium system we have to replace by del E. So this is del E over RT square. So this is our other relation, it is a relation 4. So when the system is attaining equilibrium, just plotting activation energy or energy versus reaction coordinate. So when the reactant are going to product, so they must pass to a state that is called transition state, and then they go to product. Because activation energy is very, very important, it's involved here. So just plotting this energy, that is potential energy or activation energy, we just express just general energy, and on x-axis that is reaction coordinate. So this is these are our reactants A plus B. They combine together and they go to a higher energy state that is called activated state or transition state, represented with Ts. And after that they are coming to product. In our case these are C plus D are our product. So when they are going to the higher energy state, so they must possess the energy, minimum energy, that is represented with E1. Here in this equation 4 we have del E, and that is the difference between E1 and minus E inverse. That is the energy possessed by the reactant to go to the transition state, and E inverse the energy possessed by the product to go to the transition state. and the transition state is decomposing into product by releasing or absorbing the energy, that is E minus or E inverse. So the difference in the energy between the two is represented with E. So depending on the nature, either the reaction is exothermic or endothermic, but this is a very general case. Now equation 4 can be modified for the reactants or for the forward and reverse reaction. So we can write down equation 4 for the forward. For forward case, we have d ln k1 over dt is equal to E1 over RT square. Similarly, for reverse, we can modify d ln k inverse over dt is equal to E inverse over RT square. So depending on which direction the reaction is going on, it's independent, but the transition state is always the same. Either it is formed from product or the reactant, so it doesn't depend on the direction. Now we are taking the just going explaining this in terms of Gibbs free energy. We already know that in thermodynamics that the Gibbs free energy change in Gibbs free energy is equal to minus RT log equilibrium constant, or rearranging this one, just taking log K is equal to del G minus del G over RT, or just taking K outside and just taking exponential, so e raised minus del G over RT. So this is our constant. We have one equation, is equilibrium constant is equal to e raised minus del G over RT. So this is some kind of equation 5. We already know from thermodynamics that the change in Gibbs free energy is equal to the change in enthalpy minus T into change in entropy. So this is another kind of relationship we can put here, but later on. This equation can be modified for the forward and backward reaction. So we can modify the Arrhenius equation. This is some kind of analogy to Arrhenius equation in which K is equal to A e raised minus EA over RT. But here we have replaced the activation energy with the Gibbs free energy change for the reactant to go to the activated state or transition state. So by analogy, we can write down for the forward reaction, modifying this relationship for the forward reaction, just putting the Arrhenius constant on these are cancelled for the forward and reverse because both are the same. So K for the forward reaction, K1 is equal to E raised, or we can write down just K1, and this is minus del G going to transition state. In the forward direction, we have to write down only 1 here in substate over RT. And for the reverse reaction, we can write down K inverse A inverse E raised minus del G, and this inverse RT. We know that this constant for forward is equal to reverse. So these can be cancelled, and our equilibrium constant K is a ratio of K forward over K reverse is equal to, if you put the value from these, so that is minus del G for forward reaction over RT, that is our divide by, so in division it will become plus for the reverse reaction, so E raised plus del G transition state inverse over RT. Just putting the value of del G, so after putting the value of del G, so we have K or K forward over K reverse is equal to So E raise minus del H minus T del S over RT, and this is E raise, this is plus del H minus T del S over all RT. Just separating the term, so E raise the enthalpy term and the entropy term we can separate. So just taking the entropy term, so we have T is common in both, and this term will positive become plus, minus into minus, and this term is already minus. So this is actually for the forward direction, so we can write down here 1, and this is for the reverse, and this is minus. Just transition state for the forward direction 1, and this is minus for the reverse direction. Entropy change divided by RT, so T will be cancelled with each other, and we have only R in the denominator. In this case, we have this E, and this is minus del H, and this is for the forward direction, and this will be positive plus del H for the reverse direction divided by RT. So we have finally E is del S star forward direction minus del S star reverse direction over R, and here it is minus del H forward plus del H reverse over RT. We are mostly interested in the forward reaction. So in chemical kinetics, we are mostly interested in the forward reaction. So just taking the forward reaction rate constant, so K forward reaction will be just taking for the forward reaction, or putting the value for the forward reaction. So we have A forward E raise del G minus del G, and that is for the forward reaction over RT. So after putting the value in this, we will get K1 is equal to A1 E raise. Just putting the value, so we have minus del H star for the forward direction, and here we have to write down RT. In other case, T will be cancelled, so E is. So we have the minus sign, so minus will become plus. So we have plus del S star for forward direction over R, or in log term ln K forward is equal to ln A1, and these are the terms minus del H1 for the forward direction over RT plus del S1 over R. So these are the different forms. So this is the log form and this is the exponential form. So these equations are called Eyring equation, Eyring, Eyring equation, which explain the effect of temperature on the rate of equilibrium system. In this case, if we plot log K1 versus 1 over T, so the slope, we will get a straight line, and in the straight line the slope will be equal to del H1 over R. So this will be the slope value, and where del S1, this is the entropy of transition entropy, and this is a very important entropy for the forward direction. So this is called transition entropy. So this was quite nice information about the effect of temperature on the rate of reaction. Hope you understand. So try to derive this equation and compare with the text.